So let's start from this stochastic equation and let's discuss what it means, and then we will move from there. Okay, so for those of you who are not familiar with this, I would say this. If we go to the infinitesimal version of this equation, it's that if you are interested in a trajectory that is x of t, is something that lives in a space, in R3, whatever you want, and it's a continuous, even continuous trajectory. You see x of t. It will be a random process, so sometimes I call it random process, I will put it a little w, all right, the classical notation. And sometimes I will remove w to express the fact that it is a realization. That is, you start from here, you generate something on your computer that goes like this, and you do another realization, so I'll indent it with w, okay? This is a classical stochastic process. So let me know, sometimes I'll put it, sometimes I will not do it. Okay, so what is the meaning of this equation? So let's think about looking at what happens between time t and t plus delta t. This is this difference, and this can be looked at b of x of t multiplied by delta t plus sigma of x of t multiplied by w of t plus delta t w of t plus delta t minus w of t. So let's go step by step. W of t, since everybody agrees that, when I ask, this is called a Brownian motion. This is called a Brownian motion. Brownian motion. The increment, so Wt plus delta t minus Wt, is usually thought, this is a stochastic, a Brownian variable with variance, so it will be of variance, this can always be written, I will write it this way, 2 delta t, square root 2 delta t, psi, where psi is a Brownian, it's a random variable, it's a Gaussian variable, so of mean 0 and variance 1, and then I will write it this way, 0 and 1, which means mean 0, there's no drift, mean equal to 0, and the variance is equal to 1. Again, so a Brownian variable, a Gaussian variable, is characterized basically by only its second moment, which is the square of this, of the expectation, right? So this is how actually you generate on the computer your Brownian increment here. So you have increment that depends on delta t. If in general you can also have, I will also write it this way, 2 delta t d, where d is a diffusion coefficient, where d is a constant, and this is called the diffusion coefficient. Diffusion coefficient. So basically, the increment of the position of the trajectories between time t and t plus delta t is due to the drift with a time scale delta t. Sigma here, so b and sigma, they are deterministic functions. They are deterministic functions. And this is just the increment. And so the infinitesimal version of this can be written this way. So again, when you see this equation written, you have to think instinctively of this, and this can be written this way. This is delta x. And the infinitesimal version is when the delta here become d. So you get, let me write it one more time. So this is d of x equals d of x of t plus sigma x of t d omega or d omega t, right? And this is delta t here. So again, you can also write it this way. If we divide everything by delta t, we get dx dt. You write it this way. And here you have d omega dt. And again, we understand where it comes from. You know, when you have this, you multiply everything by delta t. And this is the meaning of this equation, which you can also write x dot. So this is again notation, x dot. And this is called w dot. So when you see this, you have to think this is the discretization version for numerical application, or this is the infinitesimal version. Now, how do you so in general, what can we say about this? What is the meaning, for example, of solving an equation? Okay, if there is no noise, what is the meaning of solving an equation? Yeah, you integrate the equation, and this is known since Cauchy. You know that if you have and this is why I skipped all the part about dynamical system. So so we understand what we are saying. If sigma is 0, we have x dot equals d of x. And this is a classical dynamical system. And already from this is already very hard to solve. We don't know how to solve it in general. There is no simple theory. That's why people looked, for example, at what happened near critical points, where you can say that you have an attractor where you're in dimension 2, so all the trajectory converges. They can also converge this way. And you can also have not only, you have more of the dynamics. You can have limit cycles, you know, where trajectory comes and don't converge, but they do. Or rotations, they also, what people have found 40, 50 years ago, there's a strange attractor where you can go around one part of your phase space and then switch to another part and oscillate, you know, between the two. This is called the strange attractor, you know, characterized, it was the Lorentz attractor. So there has been a huge school about dynamical system, and it's not my goal to repeat all what people have developed. And you know, for example, what you can find most of the time when you are studying biological questions, if you have dynamical system with a parameter lambda, that is for lambda, when lambda is changing, you can have it's an attractor and suddenly it comes into a limit cycle. You know, this kind of off-type bifurcation. But this has been well documented. So solving an equation like this means, in general, that you start with, let's say, an initial condition. So solving the equation, so this is, I'm not going to describe much, but for example, this is the theory of Cauchy, which say, and again, I don't want to go into this, but basically if you give an initial condition, and if this system is sufficiently regular, then you know that you can find a unique trajectory going through this point up to some times. And the most difficult part is, of course, for example, if you want to look at long time asymptotics, how things behave. And we don't know. We know that it exists, but usually we have to work on it to know how what's the behavior. All right. So then, if B is regular, and the Cauchy theory said there exists a trajectory that is a continuous function that goes from a certain interval, open interval in general, to the space you're interested in, and x of t will be your trajectory. This is a solution. But studying the limit of Riemann, the behavior of x of t for long time asymptotics is unknown. So the behavior of x of t for t large is usually unknown. Okay. So now we add noise. Okay, this is I'm not going to enter this is classical. Now we want to add noise on this. So what is the notion of solving an equation when you add noise? There is you can generate trajectories, right? But so the concept of probability that you all know is that you are interested in the statistics ensemble, which are characterized by what is called the probability distribution function. Okay, so this is the shift from deterministic to stochastic. That is, now we are interested in, associated, so this is very important, the parallel I'm going to draw now, because this is the link, fundamental link between the individual description to the collective description. So to characterize the stochastic equation, stochastic dynamics. So, and we will see it is equivalent. We use the probability. So I write it probability density function, which is called the PDF, which is P. So what is it? This is the probability to find the particle at position, let's say y plus dy, conditioned that at 0, let's say the particle at position x. And this probability can be written as P, let's say x, y, and t. And this reads, we have to understand what we're talking about, the probability to switch from x to y in time t, and this is multiplied by dy. That's why this is the density. This is called the density. Right? So this is a characterization. So if we know P, what does it mean? It means that if you start, so suppose you have a domain, you start at position x, and you'd like to know when are you going to switch, what's the probability that at time t, if you take a picture, your trajectory will be inside this box around y of volume or surface of volume element dy. Right? So this characterizes fully, and we'll see when we'll do the Fokker-Planck equation, this characterizes fully the dynamics. However, we are not much, we haven't win much if we don't know how to calculate this. How do you calculate the probability distribution function? Most of the time we don't know. So a hard question is how to calculate, how to compute. First of all, we have to derive the equation. How to compute the probability distribution function. So most of the time we can't, nobody knows, and that's why people are using simulations or asymptotics. You see, the idea is that if the particle cannot escape the domain, you understand that this is a hard question because the geometry of the domain is important. If the domain is very narrow or very big, it will affect the probability to find the particle here. So if it depends on the geometry, then that's why you need to use here partial differential equations. It's not something that we can escape from. Okay? So this is an important point. Now, let's move on to the idea of integration. So why, again, I'm showing you all of this, because I would like you to connect and not be afraid to look at the tau calculation and all the properties that people have derived, because they are very important. You should look at this as a background. So we'll see later how to calculate this. Now the question is how to integrate. What is the meaning? What is the meaning? What is the meaning of integrating equation 1? This is equation 1. So for this, if we just do what you want to do, you just take delta t over there, and you integrate. So we would like to make sense of x of t minus x0. And we would like to say this is the integration from 0 to t of b of x of s ds, plus integration from 0 to t of sigma of x of s d omega of s. Okay, so what is the meaning of this? I just integrate formally. So if you think about something in dimension 1, if you have a deterministic term here multiplied by ds, this is a classical integral. Think about Riemann integral. Now the question is, what is this? What is this term here? What is the meaning of integrating something with respect to a Brownian motion? So the same way as the Riemann integrals has been developed by using the sums, when you cut an interval into pieces, we'll do the same here. And the question is what we'll get, and this is called the stochastic integral. That's it. So is this all of this completely new for everybody? Is it too easy, or shall I go faster? Or it's a good speed, and people, and it's okay. Yeah? Okay. So I'll go step by step for you to see the different step of understanding that. All right? Okay. So now I would like to introduce, this is the first and the last class, I'm going to introduce spaces, like abstract spaces, to understand what is the meaning of integrating with respect to this Brownian. And again, I do that so that you should not be afraid to look in the math literature, so that you get all kinds of properties you are interested in, and you understand what this literature can bring you, how it can help, or maybe that you are wasting your time. But it is important to understand it, to have this knowledge, to see. Most of the time there are very interesting properties in the math literature, and you need to see if it's suitable for you or not. Okay, so for this, if you decompose, if you have no, so what I'm going to do now, I will decompose the interval 0t, go from 0 to t. And now you slice it. T1, T2, up to Tn minus 1, Tn. And let's say this is over time, it's unimportant that it's fixed, but let's suppose this is delta t. So you have Tn equals t, which is n times delta t, right? So we cut all of these intervals, and we would like to decompose this and make the integration on each of these subsegments. So basically, if sigma is 1 here, what is the meaning of this integral? So we can look at it as a sum of omega tk plus 1 minus omega tk, and this is for k from 0 to n minus 1. If you replace this by these sums and you look at the limit when delta t goes to 0, you'll get a sum that should be studied. Again, so what I did, I take this part here, I suppose sigma is 1. I said I would like to calculate the integral from 0 to t as the classical integral, where you use the Riemann sum. So Riemann sum is what? Suppose you have a function, right? You just look at your square here. You can approximate it. There's many ways to approximate it. You take the approximation by the square, you let the square goes to 0, and delta t goes to 0. You have a sum that converges to infinity, and it should converge to the area. This is the classical construction of the Riemann integral. So what I'm saying is that we're going to do the same here. We're going to look, except that we don't have here a deterministic function, we have a stochastic function, right? But so we still have the sum of Brownian variables which are independently distributed, and we would like to study the sum in general when we'll have then a function here. So for this, I'm going to show you a framework, a frame to study this integral here through this calculation. So I'm going to introduce what is called the space of non-anticipating functions. So again, I'm doing all of this because I think it's important. It's maybe the part that is the most heavy part in terms of analysis of the class, but I think, again, this is what we have to discuss. So this is the space of functions that are stochastic processes, such that the f omega t, this function is independent of the increment of omega of t plus s minus omega t for all positive s. For all s positive. Basically, what that means is that this point at a time fixed time t doesn't depend on any stochastic variation of the future. That is, this is independent of what happened for the future, that is for all this increment. So this is the increment. For example, if you think about s as delta t, a small increment, this should be independent of this. That is, I consider all the class of function continuous, so this is independent of this. And this translates, how do you write it in terms of probability? What is the meaning of these words in mathematical symbols? To be independent means that if you average all of this increment with the weight of this function, what does it give? I'm sorry?
The product.
The product, and the product is?
Decomposes.
Yeah, and since what is the expectation of this Brownian motion? What is the mean? Zero, that's it. So this means that the expectation of f omega t, I'm going to write it once, so you understand how this translates mathematically. You all know what is the meaning of, this is a symbol of expectation, your average over realization. Your average over this little omega. So the fact that it is independent can be written the following way. This is f omega t expectation multiplied by the expectation of omega t plus s minus omega t. Why? So whatever okay, there is one more thing that I have to tell you, is that this ensemble of function has to have finite energy. So I'm going to just in 1 second to give you another condition, but suppose this is finite, this is not infinite, this is finite. Then the expectation of this, if this is a Gaussian of mean 0, because the mean is 0 for this expectation, this is S, I call it delta t, since the mean is 0, the mean of this is 0, so all of this is 0. Okay? So this is, and the space I'm interested in is going to call H2 of 0t. This is the space of all the function f in this ensemble S, such that the energy, the integral itself from 0 to t, of the expectation of f omega square of S ds, this is finite. Right? So this is a space of functions such that they have a finite, so expectation of this is a deterministic quantity, which is integration from 0 to t, it is finite, doesn't blow up. And now if we would like to calculate for this space of function, I would like to give a sense, make sense, for calculating this integral. we're just putting a framework to say when we can calculate this, when this makes sense to be calculated. And we will see that when we have a function like this is okay. It falls into this result, into this framework. Okay, so now let's do this calculation for a function f that are piecewise constant. So I suppose I take a function f which is piecewise constant. What does it mean? It means that if I take the interval 0t, the interval that we have here, sometimes I call it little t or capital T, it's the same t. And now suppose it is piecewise constant, that is, you cut it, you slice it, and you have a function that is constant on each pieces. And so it's the function f restricted to the interval tk plus 1 is equal, let's say, to a constant fk. And this fk, we can call it fk of omega. It can be a random variable. It's not necessarily a variable deterministic function, right? Each time you have a realization, you have another number. But once you have a realization, this is fixed. So you have, this is, for example, f1, f2. So think about it like, and so now I'm going to tell you that the integration from 0 to t of f omega of s d omega of s, I'm going to show you this approximation and show you that it works. That is, if we then look at different type of discretization, it will work for a general function that is not necessarily piecewise constant. So you have a function, it is piecewise constant, and let's say that for this function, f, we look at, so this is tk plus 1. So for this piece interval, this is fk, and now this is omega at point tk plus 1 minus omega of tk. And we have to sum from 1 to n. Okay? So I will have the notation that omega k is omega of tk. So what can we say about the expectation of this integral? That is, the expectation of this, of all of this equals the expectation of all of this. And by definition, because of this increment is independent, this is exactly what we have written here. The expectation here is the sum of the expectation of the product, which I'm not going to rewrite. Okay, I will write it now. Fk, and this, put it here. This is 0, so this is 0. And now, this is me again. Yeah, so it has. And now, what is the expectation of the square? Now, if I take the integral from 0 to t of f omega of s d omega square, I put a square here. What is it? Okay, we have to see that this squared is, I just calculate this square, right? And so let me write it here. This is the expectation of the sum for k, the sum for q of fk f q of d omega k d omega q, where by definition omega k d omega k is omega tk plus 1 minus omega tk. So what is the expectation of all of this? Using the same property of the fact that Fk is independent of this, I can take this expectation, take the expectation here of this product, multiply by the expectation of the product d omega k, d omega q. Now what is the expectation of the product of d omega k, d omega q? So for this, we have to remember that the increment d omega k, d omega q are all independent. So if omega k is if k is different than q, since they are all independent, then this product, the expectation of this product is 0, except when k equals to q, because then we have exactly this squared. And if we have this squared, so let me put it here, if you have this squared, this is this squared. And now we have to take the expectation of this, which is the expectation of this. And what is the expectation? So, what is the expectation now of, so 2, yeah, I can put it out for the expectation, it's deterministic number, delta t also, d also, and you get what? You get expectation of psi squared. Now what is the expectation, what is this? This is simply the variance, and the variance is equal to 1. So this is just 2d delta t. So this is simply 2, so 2d, what is delta t here? This is exactly tk plus 1 minus tk, multiply, so maybe here, wait, there's a factor 2. Yeah, maybe here we have to take variance 1/2. I take this variance 1/2 here so that I can get rid of, take the d omega k, let me decide that the diffusion coefficient here is 1/2 here. So that d multiplied by 2 is 1. So then what you get from here is a sum of expectation of fk squared, tk plus 1 minus tk, and for k going from 1 to n. And now what is this? Expectation of a function. This is a deterministic function. Tk plus 1 minus tk, this is a decomposition of your interval. So when t goes to infinity, if the delta t goes to 0, this is the classical Riemann integral. So this converges as n goes to infinity to the integral from 0 to t, capital T, of expectation of s square ds. And by definition, since I am in the space where this is finite, this is convergence exists. And again, I'm not going to all the proofs. This is to understand that to calculate this quantity, we cut. So we did it for the piecewise constant function. And now, I'm not going to prove more theorem, I'm going to state it, however. So for a general continuous function, so now if you have a general continuous function, so for any function f in the space h to 0t, so this is any function of this, there exists a sequence of piecewise constant functions. So this is an ensemble of functions such that this function converge in the L2 to f. So what does it mean? That is that fn minus f in the norm h h20t, this converges to 0 when n goes to infinity. That is, take any function of this space. For any function of this space, you can always you cut in n steps, you approximate the value of this. It's a continuous function, so you can approximate here by the classical, constant value of the classical Riemann, which I'm not going to do. And you can prove, which I'm not proving here, that any of these functions, there is a sequence. As n goes to infinity, so you can refine here your step, converges to f in the sense that the norm defined here by this space here, which is h2 norm, I'm sorry, this means here, this is the meaning of this. This is f of norm. This is the norm here. So f omega minus f omega minus f means you take the expectation of the difference of the function minus the limit, and you square it, right? And so in that case, for all this function like this, we can extend the stochastic integral f of s d omega of s as the limit of the integration from 0 to t of this family of functions that will converge almost everywhere, and more important in this h202 norm, d omega s. So we have extended the stochastic integral for any piecewise constant function to any continuous function, which are not necessarily constant. All right, so this is the limit when n goes to infinity. Okay, so this gives us definitions, and so we can show, you can prove, right, that for any, this doesn't depend on the on the slicing that you are doing. Any kind of slicing will work. You go to this limit. So this proof can be shown. It is given in the classical book of Ito Makin. So this is given in the classical book of Ito Makin, this is in Springer, 69. That's why I'm not going to redo it. This is classical, but I wanted to show you all of these steps so you understand what we're talking about, and more important, that what is the meaning of making this integration sign here. It means that we go to the limit and we are manipulating here a stochastic process. Okay, so yeah, we have time. Now I'm going to move on, and I would like to now we have discussed all of this. I would like to introduce the Langevin equation. Now we understand what is the meaning of integration. Now we can discuss about stochastic equation, and we can go to the integrations. And now I would like to introduce the Langevin equation and the Chandrasekhar approach, which again, we're going to repeat some of this here, but that's fine, so that you understand what we're going. And in addition, we will prove what is called the fluctuation dissipation theorem. Okay, so I want to do that now, and then we will be able to stop, I think, because this will be for next week. And next week, I'll go back then to the Ito calculus. So next week, I'm going to show you, so keep that in mind. We'll do a little break in this direction, but next week, I'll show you the Ito calculus and the difference for those of you who have never seen that. If you have two stochastic processes like this, let's say x1 and x2, which satisfy a stochastic equation, then the product D, the same D that we have understood and seen here, this, if x1 and x2 are deterministic function, you know that dx1 x2 is x1 dx2 plus x2 dx1. Right? This is what you have learned in elementary calculation. So we see that this is wrong. This is not true anymore, and it comes from this calculation. And the term that is here, the new term, is very important for the calculation of the mean first passage time and the Fokker-Planck equation. This is this difference that comes from this calculation. That's why I want to spend, sometimes to make sure that you all understand this. So this is for next week.